so the main thing I want to do today is talk a little bit more about orbit spaces and mostly see some more examples. So the setup from last time, recall, so we have G group acting on a space X. And we define, so O sub little x is the orbit of X. So this is all the points you can get to by applying some element of G from little x. And we have X mod G, which denotes the collection of orbits. So together these give a partition of X. So this is called the orbit space. We view it as a space with the quotient topology. Okay, so like I said, the main thing is going to be to look at several examples of this. So the first example, I want to describe how you can think of the Klein bottle as an orbit space. So here we're going to take X to be the plane, and G is going to be a certain subgroup of isometries of the plane. So this is the group generated by two isometries of R2. And what are they? So they'll be called A and B. So A acts by a translation. So it sends XY to X plus 1 Y. So just it's a horizontal translation. And B is, well, what we called in the last discussion section, a glide reflection. So it translates in the Y direction and reflects in the X direction. This is a glide reflection. Let me draw a little picture for how these things, how you can sort of visualize these isometries. So draw R2 like this, and yeah, let's just consider what A does to like the unit square. So let's label these points 0, P, Q, R. And so, okay, well, A just shifts everything to the right by 1. So the image of this under A now is this square like this. This is A of P, A of Q, and so on. Okay, and then let's contrast that with how B works. Let's take the same unit square and look at its image under B. Let me draw this here. So we take PQR, vertices, let's track what happens to them. So, right, so we translate vertically up and then reflect horizontally. So P gets sent to, let's see, 0 just gets sent up. So under B, this is B of 0, and here's B of P. And now, so R gets shifted up and reflected across the y-axis. So here's B of R, and B of Q is here. So now we get a square on the other side of the y-axis. And well, the orientation has changed. So if we had labeled this like this, then the image looks like this, whereas here the orientation is the same. Okay, so that is, that's our group. Our group is generated by these two elements. So let me point out, so note that A and B don't commute. So in particular, this group G is not isomorphic to just Z squared. And you can see this, well, you could see this maybe in a variety of ways. You could just draw the pictures and like just see where the unit square goes and see that it's different for AB versus BA, or you could just write down this composition, the two compositions. Maybe I'll let you check that. Oh, but on the other hand, let me also mention that B squared, so if I do B squared, so this is B applied to, so minus X, Y plus 1. This is, so I negate the X coordinate again, and then Y plus 2. This is a vertical translation, which does commute with A. So it does commute with A. So the subgroup generated by A and B squared, this is isomorphic to Z squared, and it's a subgroup of G. Right, so you have the subgroup which just translates. Okay, so all of this is just meant to give you a little bit of intuition about this group. Now let's figure out what the quotient is. So let's determine the orbit space. Well, the first observation is that, well, so observe that every point in R2 is in the same orbit as a point in the unit cube. So, I mean, we have a tiling of the plane by unit cubes. And, well, yeah, I mean, I think I said something similar like this when we looked at the torus as an orbit space. If say this is the origin and you start with some arbitrary point, then, well, by applying some iteration of B and A, you can sort of move the X and Y coordinate so that the point lands somewhere in this region. So what that means, so this implies that there's a surjection from the unit cube to X mod G, the orbit space. And let me actually say one more thing. So yeah, every point being in the same orbit as some point in the square means that this map is surjective. Here I'm just restricting the, this is the restriction of the map from R2, from R squared to the orbit space. But we can say more. Let me rearrange this. Right. So we can say more. So also, well, sorry, actually now I changed my mind. Let me move this back. Sorry. So, I mean, what this tells us is that what am I trying to say? Yeah, right. So X mod G, the orbit space, is topologically equivalent to the partition, the associated partition of the cube under this map. Right, so this is something we showed last week. We had a theorem. If you have a quotient map, then the codomain here is topologically equivalent to the partition for the partition for this map. Okay, sorry. And so, well, if we want to identify this quotient, let's just think about what partition we get here. And the first thing to say is that, well, no 2 points inside the interior, in the interior of the cube are identified, are in the same orbit, because, well, A moves things outside. A and B both move, you know, these cubes are translated. And so the only identification, you know, the pre-images, this is the partition where we look at Q inverse of A in X mod G. So for most points, the pre-image is just a single point. The only situation, the only case when is the orbits of points that are along the boundary. And what we find is that, well, under A identifies the left edge with the right edge of the unit cube, and B, so under B, this bottom edge, which I'm thinking of as this edge here, this edge under B gets sent to this edge. And then by applying A, we can send that to this edge. Okay, so the bottom edge and the top edge get identified by a reflection. Okay, and so that we see that we conclude that, well, X mod G is topologically equivalent to this space where we take the cube and we identify the sides like this, which is exactly the Klein bottle. So a general remark about this strategy, the strategy that we used here to identify this quotient space. So here's a general strategy. For identifying a quotient space. So the first step is to find a subset F in X. So here, quotient space X mod G that contains a point in each orbit. and possibly more than one point on the boundary of F. Okay, so in this previous argument, the unit cube, I was calling it a cube, but I guess I mean the unit square is serving this purpose. And F should be as small as possible. Right, so in this example, we just observed that R2 is tiled by translates of this unit square under the action of G. Okay, and so this is our set F in that example. And F is sometimes called a fundamental domain. And right, so this smallest possible, well, yeah, let me not say too much more. I mean, for points, you want F to be some open set, or well, for points in the interior, you don't want any two of those to be under the same orbit. So, I mean, in examples, it's sort of clear how this works. So let me not sort of spell it out in full details. So once we have this situation, then, well, this first condition implies that there's a surjective map from F to the quotient space, the orbit space. And so it suffices to determine the induced partition. Partition of F induced by Q. And this is what we did here. So we started with a group action on R2, and then we said, well, really, we can think about the orbit space as a quotient of this fundamental domain, the square, and then we looked at that quotient, and we see how the sides are identified. So here, i.e. how points on the boundary of F are glued. Okay. Okay, so we'll see another example of this now, how this can be used. All right, so example 2. So these spaces, so this is a new space, a collection of spaces that we haven't seen before. These are called lens spaces. And they're obtained as orbit spaces for a group action on the sphere, three-dimensional sphere, which, so this is the unit sphere in R4. But for this construction, it's useful to think of R4 as C squared. So these, in this case, S3 can be described as pairs ZW, pairs of complex numbers, so that, well, the norm of this is 1, which we can write in this way, where bar here is complex conjugation. Yeah, so if Z is X plus IY, where X and Y are real numbers, then Z bar is X minus IY. Or maybe more helpfully, if we write Z as in polar coordinates, R e to the I theta, then z bar is re to the minus I theta. So for example, S3 contains points like, well, you can have a point like e to the I theta 0, or 0 e to the I phi, say. So there's these two copies of the circle sitting inside S3, but there are other points like, well, points like this. Okay. So now the group action. So the group here is going to be a finite order cyclic group. So we're going to denote the generator by T. So here I have a single generator, and its pth power is 1. So here P is any integer, positive integer, and we're going to fix Q between 1 and P with the GCD of P and Q is 1. So these are relatively prime. And now we'll define the way T acts on ZW. And it's defined like this. So we take, we multiply Z by 2 pi I over P, and we multiply W by e to the 2 pi I Q over P. So note that this sends the 3 sphere to itself, since, well, you can check that. Since this has norm 1, then when you write down this expression here, it cancels. And moreover, right, so if for this to be a group action of Z mod P, we want T to the P to be the identity. So if we take T to the P acting on ZW, this is like, well, we multiply P times, so this is e to the 2 pi I times Z, and e to the 2 pi I Q times W. But of course, yeah, this e to the 2 pi I is 1, and so this is the identity map, T to the P. Okay, so this group action, one way to think about it is it's a homomorphism from Z mod PZ into the group of topological equivalences of the 3 sphere. So the quotient X mod G is called a lens space. And is denoted, it's usually denoted LPQ. Okay, so these are interesting examples. Let's think about some specific cases. Well, one in particular. So let's look at P is 2 and Q is 1. So if P is 2, Q is 1 is the only option. So we're looking at an action of G is Z mod 2Z on S3. And the generator, how does it act? So, well, it acts by multiplication by e to the 2 pi I over 2 on both coordinates, because Q is 1. But e to the 2 pi I over 2, that's e to the pi I, which is minus 1. So this is minus Z minus W. So this is the antipodal map. So we know what this quotient, so this is a familiar example. So X mod G is the projective space, RP3. So, or I guess I should write it this way. So L21 is the same as RP3. So I want to tell you how to think about the general case. Let's do it still in an example. So let's take P to be 6 and Q to be, so we have to choose something relatively prime. So we could either choose 1 or 5. Let's go ahead and choose Q to be 5. So once we do this example, this will explain the general case. And what we're going to do is, so we'll, well, yeah, so let me give you the punchline almost. So we'll describe L65 as a quotient of, so the picture is going to be the following. So you have a hexagon, and then you take, well, you take the cone on the hexagon. Let me put this point here. So then there's points back here. So, okay, you take the cone on the hexagon. And did we discuss the cone? I can't remember if we did. It is discussed in Armstrong. But okay, the cone is this operation. You just take an extra vertex and then you connect every point. This is a solid hexagon, not just the boundary. So this is a solid region in R3. And then you do the same on the bottom. So you take these two cones and you glue them. And right, so the statement is, we'll describe L65 as a quotient of this space. So it's some three-dimensional object obtained by gluing. We're going to be gluing faces of this polyhedron to get the lens space. Okay, so now let me sketch how this works. So I mostly just want to give the idea. Right. So for this, it's helpful to think of the sphere as what's called the join of two circles. Right. So first, before I say any more, I mean, the strategy for describing the lens space as a quotient here is the same strategy we took in understanding the Klein bottle and this general strategy that I was describing here. So we want to find some region in the three sphere so that under the group action, this region just gets translated into disjoint pieces, maybe with the exception of how it gets mapped under the boundary. and that will give us these face identifications. Okay, and right, so it's helpful to think of the three-sphere as what's called the join. And the join, so this is a general operation that you can perform on two spaces. Let's assume that, yeah, so let me describe this. So suppose we have two spaces, one is in Rn and the other is in Rm. Then there's this operation called the join where you can take, it's a subset of now Rn plus M plus 1. No, I guess Rn plus M is okay. And the way it's defined is you join every point of X to every point of Y by a straight line segment. So let me do an example which is lower dimensional. This example is a little hard to view, but by the way, these two circles in this example are exactly the circles that I was describing here. So here you have, this is a copy of S1, and here's a second copy of S1 sitting inside the three-sphere. And the claim is that you can think of the three-sphere as the join of these two subspaces. So a lower dimensional example that's nice to think about is if we take, let's think about the join of the zero-dimensional sphere with itself. So the zero-dimensional sphere, these are points, distance, unit distance from the origin in R1. So here's the zero sphere, and I want two copies of the zero sphere. And I take the join. So the join, by definition, I'm supposed to add a line joining every pair of a red point to a green point, of my red zero sphere to my green zero sphere. And well, so that's this picture. And what is this space? This is topologically equivalent to the circle. So in fact, this example here is, well, these two examples fall into there's a general pattern that if you take a P sphere and a Q sphere and you join them, then you get another sphere of dimension P plus Q plus 1. Right. So, okay, so I'm not going to prove this statement or this more general one, but there's this description of the three-sphere in this way as a join. And so let me draw a picture. Maybe I'll keep that there. Well, okay, sorry. Let's do a new page. Right, so here's a picture of how this join works. This is kind of a schematic picture, but it should be helpful. So here I'm going to label these points as, so these are two circles. This circle is going through infinity. I guess I'm thinking of this as living in R3, and the three sphere is R3 with an extra point at infinity, which is not drawn here, but okay, so this is a circle that goes through infinity, this vertical line. And so this circle, I'm going to think as the circle of points in coming from the second factor, and this one is the first factor, where the second coordinate is 0. And right, so now I just want to think about how the group acts on these two circles. And actually, I'm just going to focus on the vertical circle. So G acts on the points e to the I theta 0 by, so the generator sends this to, so remember the formula, we multiply by a pth root of unity. So 2 pi I over p. So when we multiply, we just add. So this is, well, okay, yeah, so that's the formula, but let me just say it this way. So as a rotation of order p, so the picture, we're thinking in the case when p is equal to 6, and the generator T just rotates the circle by 1 notch counterclockwise. And similarly, so G acts on this other circle, 0 e to the I phi, as a rotation so yeah, so this is, yeah, so let me write this more precisely. Rotation by 2 pi over p. And this is a rotation by 2 pi q over p. So in our example, we took q to be 5. So here the picture is this point gets sent all the way around to this point. Or you can think about it as a rotation clockwise by 1 tick. Okay, so now we're almost there. We're almost there. We're one picture away, and I only need to understand the picture that I've drawn in my notes. Right, so let's just draw. So here we have, yeah, so, well, okay. Yeah, let me reproduce this picture in my notes. So this segment of this circle is going to correspond to a fundamental domain for this rotation action. So ultimately, we're trying to find a fundamental domain for the action of Z mod P on the 3 sphere. And so we're going to understand that by sort of understanding first, we have this vertical circle, and we know that if we just restrict the action, then translates of this green segment cover the vertical circle. Okay. And well, since we have this description as a join, we see that, well, if we just consider all of the points that connect any points on this this green segment to a point on the let's say the blue circle here. So that gives a subset of the three sphere. And what we see is that, well, since by the way we chose this green segment, any point on S3 is obtained from, so it's by the way we chose the green segment and by this description of the three sphere as a join, any point on S3 is equivalent to, is in the same orbit as some point drawn in this picture. Okay, this might be, well, something you have to stare at the picture or think about a little bit more to understand. But this is exactly what we want. So this means to understand the lens space, we just have to understand how the faces of this polyhedron that I've drawn here are identified. And well, we know how this works. So as you translate the green, so under T, this yellow point, let me draw in yellow, this yellow point is identified with this point. And like this yellow segment is identified with, let me draw this yellow segment, is identified with this other yellow segment. Okay, so piecing all of this together, we can see that like this triangle here is identified with, well, this vertex goes up here and this edge goes over here. So it's identified with this triangle here. Okay, so this gives you the face identifications. Right, so let me just say this in one sentence if I can. So L65 is the quotient of this shape obtained by gluing the bottom triangles to the top triangles by a 2 pi Q over P shift. Okay, so that's what we saw here. Okay, so this is an example that is, well, it's an important example in topology, these lens spaces, and they generalize the projective space. And let me also remark, so this construction or argument also gives a cell structure to L65, or I mean, in general, this same type of argument works. Okay.